Hi students, today we are going to learn about Biot Savart law in Magnetostatics 2. So before going to Biot Savart law, let us know what is meant by steady currents. We all know that stationary charges produce electric field that are constant in time, and therefore we call it as electrostatics. And in the same way, steady currents produce magnetic field that are constant in time. That is the base of what is called a magnetostatics. Steady current is a continuous flow of charges that has been going on forever without any change and without charge piling up anywhere. So it's constant. The charge flow is constant there. So when a steady current flow in a wire, we know the magnitude of I is constant. Therefore, no charge piling up in any portion of the wire. So we can write dou rho by dou t is equal to 0. So then the continuity equation del dot j equal to minus dou rho by dou t is equal to 0. So for a steady current, we can write the continuity equation del dot j equal to 0. Okay, so now we know what is meant by steady current. Now, the steady current produces a magnetic field that is constant in time. But how much magnetic field? If there is a conducting element, if there is a conducting wire having a current I, it produces a magnetic field in the surrounding region. But how much magnetic field, on what all factors it depends, that is given by Biot Savart law. So, according to Biot Savart law, the magnetic field due to a current element, here you can see a small current element of length dl dash. Okay, so that magnetic field, that current element, and there is a current I flows through that. That is why I call it as a current element. It produces a magnetic field B. Small, this dB is the magnetic field due to this small current element. So how can you find the total current? So total magnetic field due to this entire conductor. So you can see there is a conductor having a current I. So due to a small current element, the magnetic field is dB. So the total magnetic field can be determined by integrating that over the entire length of this conductor. So B is equal to mu 0 over 4 pi integral I cross R divided by R square dl. So Biot Savart law says the magnetic field dB proportional to the square of, it is proportional to the current element I dl. It's proportional to the inverse of square of distance. It's also proportional to the sine of angle between the distance vector and the current element. So by clubbing all this, we can write dB equal to mu 0 divided by 4 pi I dl sine theta divided by r square, where mu 0 is called the permeability of free space, and its value is 4 pi times 10 to the power negative 7 Newton per ampere square. Also Tesla meter per ampere is also another unit. So that is the value of mu 0. Now the magnetic field due to this entire conductor is given by B equal to mu 0 over 4 pi integral I cross R. So instead of writing ideal sine theta, we wrote that in terms of the cross product of current and the unit vector in the direction of a distance vector. So that is why this expression. Okay, and the current, as it's a steady current flows to the conductor, we can take the current outside the integration, and then we can write this as integral dl dash cross r cap divided by r square. So this gives the expression for the total magnetic field at any point due to a current carrying wire. Now, as an application of this, we can find the magnetic field due to a long straight wire carrying a current I at a distance s from the conductor, at a perpendicular distance of s from the conductor. So here is our current carrying wire I, having a current I. Now let us take a small current element of length dl, and we have to find the magnetic field at the point P. So for that, let the angle between the current element and the distance vector is alpha. So let us write the expression for magnetic field due to the small current element, that is dB equal to mu 0 divided by 4 pi I dl sine theta divided by distance square, that is r square. But now we have to rearrange or replace all these with the perpendicular distance between them. So in terms of s, we have to write. So for that, we have to rearrange all this stuff. So what all you can write is that dl dash sine alpha. dl dash sine alpha is equal to dl dash cos theta, because you can see that here the angle is theta here. So what will be the angle here? That will be 90 minus theta. That is also equal to 180 minus alpha, because it is a straight line. So this angle also equal to 180 minus alpha. So 180 minus alpha can be equated to 90 minus theta. So that gives alpha equal to 180 minus 90 plus theta. That gives 90 plus theta. So alpha is equal to 90 plus theta. So that is why here there are dl dash sine alpha is equal to dl dash cos theta, because dl dash sine 90 plus theta, sine 90 plus theta we can write as cos theta. So dl dash sine alpha is equal to dl dash cos theta. And also from this expression we can write what is L dash. In this right triangle, what is tan theta? Tan theta is equal to opposite side divided by adjacent side, that is L dash divided by S. That is why L dash equal to S tan theta. Okay. Now dl dash is equal to s divided by cos square theta d theta. So differentiating this term, we obtain dl dash is equal to this term. Also, yes, what is cos theta in this right triangle? Cos theta is equal to adjacent side divided by hypotenuse. That is s over r is cos theta. So s is equal to r cos theta. So from that we obtain 1 over r square is equal to cos square theta by s square. Now substituting all this for the expression for Biot Savart law, the total magnetic field, we get a mu 0 by 4 pi I integration IL cross dl cross r. So dl cross r is actually dl sine theta, sine alpha in this case actually, because the angle between the current element and the distance vector is alpha here. So dl dash sine alpha. I'm sorry for writing here theta. This is sine alpha here. Okay. So that is replaced by dl dash cos theta, and dl dash cos theta. So they substitute also 1 over r square is there, 1 over r square, that is substituted by cos square theta by s square, and dl dash is replaced by s by cos square theta d theta. Okay, and then that is I can write that here first, mu 0 by 4 pi and I, and dl dash is replaced, dl dash sine alpha is replaced by dl dash cos theta and divided by r square. Okay, so that is actually given by mu 0 by 4 pi I, 1 by r square is replaced by cos square theta by s square, and dl dash is replaced by s divided by cos square theta, and then there is cos theta. Okay, so that is going to substitute in this expression. So hence that, and d theta is from the integration part. So after performing this integration, what we obtain is mu 0 I divided by 4 pi s, because cos square theta cancelled, one of the s cancelled, and you can take that s outside, and only integral of cos theta remains there, and we know the integral of cos theta, we get it as sine theta, and substituting the integral limit theta 1 and theta 2, the upper limit is theta 2, so cos theta 2 sine theta 2 minus sine theta 1 is the expression that we obtain. Now, this one is an infinite long conductor, you can write, theta 1 and theta 2 will be 90 degree. One will be negative pi by 2. Theta 1 will be negative pi by 2, because as this conductor extend to infinity, it's a long conductor, this angle also extend to pi by 2 like this. And towards in this side, this also will be equal to pi by 2. This will be negative pi by 2. Theta 1 will be positive pi by 2, that is theta 2. So of substituting sine 90, it is 1. So we get sine 90, 91 plus 1, 2, and 2 and 4 cancels. That gives the final answer. The electric magnetic field due to a steady current carrying straight conductor is B equal to mu 0 I over 2 pi S. So this is the expression for current due to straight conductor. I mean magnetic field due to straight conductor. We can use this result also for finding the magnetic force between two current carrying wires. So here you can see two current carrying wires having current I1 and I2. They are separated by a distance d. So if you need to find the magnetic force between these two current carrying wires, what you need to do is, first of all, this I1 produces a magnetic field in the place of I2, and that is given by B equal to mu 0. B1 we can write B1 equal to mu 0 I1 by 2 pi distance. It was S when we proved, but here the distance we selected as D, that is why it is replaced by D. So due to this magnetic field, it experiences a force, and we know that the magnetic force experienced by second conductor is given by IL cross B, ILB sine theta. It is IBL sine theta is actually sine 90 here. So this is I2, and magnetic field is B1 produced, and L sine 90. So that is equal to, so the total you can find using integration here. So I2 is there, and B1 is a mu 0 I1 by 2 pi d, and L sine 90 is 1. So L is the integral dl is there. This expression for the magnetic force. Now the same magnetic force will be there on the other conductor also, because according to Newton's law, we know that the forces are equal and opposite. So only the direction will be opposite. This is the magnetic force on the total conductor of length L. But if the magnetic force per unit length, that is F is equal to total force divided by total length, then you will get this F. F is a small letter F there. It is a force per unit length on two parallel current carrying wires, that is given by mu 0 by 2 pi, then I1 and I2 divided by D. This is an expression for magnetic force per unit length on current carrying wires. The same result that we obtained can be used for many other situations, like magnetic force due to circular wires on its axis at the center and all that. You can try by yourself. This is only an example for that. Okay, students, thank you.